All right, now we're being recorded, so cool. Just can you please let me know if those are the 7 lectures included in your midterm?
Yes, I think all 7 lectures are included.
There are more lectures? I didn't hear the last part.
No, all 7 lectures, all of these are included.
Perfect, perfect. All right, that's great. Oh, all except the last one. So you guys don't have the clinical applications of CT. Got it. Come on, no worries. Anyways, CT is going to be tomorrow, all right, with ultrasound, inshallah. So today we're going to talk about, okay, it is included. We'll figure it out tomorrow, no worries. All right. So today we're going to be talking about the introduction to radiology and the contrast material. And we're going to be talking about radiation protection. Yeah, I think those 3 are good. We're going to be talking about those 3, and tomorrow, inshallah, we're going to be talking about the introduction to CT, ultrasound preparation, and clinical applications of CT. Now, the last 3 years, the last 3 batches had clinical applications of X-ray, which is personally my favorite part. I love the clinical aspect of radiology, and I really hate physics. So that's a bummer. But anyways, let's start. 7-inch arms taken care of. All right. You know what? Included or not, I'm just gonna explain it tomorrow, anyways. You know, so just to be sure, you know. So introduction to radiology. All right. So this is the outline, nothing to say much. All right, I remember in our exam, they actually asked us about this. So this is pure memorization really. So just remember this guy, William Conrad, whatever his name is. And yeah, the first time, like one of the earliest uses of chest x-ray was for screening for TB. Again, it was discovered on 9. This is some, you know, memorizing stuff. I'm nothing really to explain here. More. Okay, first slide that we can actually explain. Now, you have an X-ray. Let me put the laser thing on. Remember there was a laser thing. Yeah, there we go. All right, so you do need to know the dates. I remember they asked us about one date. I'm not really sure because that was like 4 years ago for me. So I can't really remember, but I remember there was a date in the exam, you know? It's like, so just be on the safe side and memorize them. Also, it's one question. So like if you want to skip them, skip them. It's just one question. Who cares really? So this is the first slide we can talk about actually. So when it comes to X-ray and how it works, you have an X-ray tube, which is the source of the X-rays itself. And then you have the image, right? So an X-ray tube and you have an image. And in between, you have the subject. And what's the subject? The subject is the patient, the human, the whatever you're scanning. That is the subject, right? So you have a source, you have a subject, and then the source will give you X-rays that will hit the subject, and then X-rays will interact with the subject and gives you an image. That's basically, in a nutshell, how an X-ray works. Now let's dig deep into this a little bit more. Why is it not working? I have to do this. Okay. So this is the X-ray tube, and this is where the X-rays are formed. You have a cathode and you have an anode. And we all know cathodes are negatively charged and anodes are positively charged. So cathodes are negatively charged and anodes are positively charged. Now what happens is there's a current, there's a voltage, you know, it gives, like, you supply it with energy, you supply it with electricity. And what happens is the cathode will heat up, and what will happen is that the cathode will release electrons. And we know that electrons are negatively charged, right? And we know that the anode is positively charged. So what will happen is that the electrons that are negatively charged will naturally be attracted to the anode, which is the positively charged end. And that's basically what happens. So it starts all in the cathode. You have an electron that travels to the anode. And when the electron hits the anode, this is when you get an X-ray. Now I'm going to talk about this more obviously, but yeah, that's basically how it works. And guys, I was told that I talk fast. So if you think that I'm fast or something, just let me know in the chat and I'll slow down. And if you need me to repeat anything, please let me know. I don't want to, go past something without everyone being on the same page. So just let me know if you need me to repeat anything. Oh, my days. Okay. So that's what I was saying. So you give the cathode an energy source, right? You give it electricity or something. And what happens is that it will heat up, and then you'll have electrons going to the anode, all right? And then the anode will give you X-rays. And that's basically how this works. This is just a slide about the electromagnetic spectrum. It just wants to tell you one thing, that X-rays are ionizing radiation, right? X-rays are high in frequency, right? And they can cause damage. Now, if you look on the other side, you have radio waves, right? And with radio waves, that's what we use in not radio waves, but like in general, on that end of the spectrum, that's where you're going to find the ultrasound and the MRI waves that are used in those modalities, right? And basically, what happens is that once you decrease the wavelength and you increase the frequency, so can you see? Look at here. Look at like this part right here. The frequency is low, so you have only 3, right? I hope you guys are getting this. The frequency is low. The more you increase the frequency, right, the higher the energy of the wave, and the higher the energy, the more harmful it is to us, right? So it's just trying to tell you that X-rays are on the higher end of the spectrum, and that's why it's considered an ionizing radiation or a harmful radiation. Yeah, and as I said, ultrasound and MRIs are found all the way here on the lower end. Yeah, that's basically it here. All right. There are 2 things you guys need to know. You need to know the kVp and the MA, all right, or the milliampere. Now, the kVp is the energy of the electron, and the MA is the number of electron. And you need to remember one thing. If you increase the energy of an electron, you will get a worse image. And contrast this with the milliampere. If you increase the milliampere, or if you increase the number of electrons, you're going to get a better quality image, right? So the higher the kVp, the higher the energy, the worse the image. The higher the MA, the higher the number of electrons, the better the image. So keep that in mind. If you want to improve the image, all you got to do is decrease the kVp and increase the MA. All right, keep that in mind, because this is going to be helpful for you when you try to understand. Can you? Sure. Okay, so you have the kVp and you have the milliampere. kVp and milliampere. Now, kVp, when you increase the kVp, you increase the energy of each electron. All right, so each electron is going to be more powerful. And when you do that, this is going to give you a worse quality image. Your image is not going to be as good. If you have a high kVp and you have high energy electrons, you're going to have a worse image. Now contrast that with the milliampere. If you increase the milliampere, you increase the number, not the energy of the electron. Not the energy of the electron. You increase the number of electrons. And when you do that, you get a better quality image. So the difference is when you increase the kVp, you increase the energy. When you increase the milliampere, you increase the number of electrons. So keep that in mind. Yeah, that's basically what this slide says. All right, so now in X-rays, you have yeah, that is the chair. So 1 second, guys. This should be better. Inversely proportional, not really. I mean, there isn't really a relationship between them, you know. Physics-wise, there's no relationship between them. They are separate, they are independent. You can increase the kVp and the MA. You can increase the kVp and decrease the MA. So they are not really connected in any way. So you can't really say that they are inversely proportional. In their effects, yes, but they are not tied together, you know? Like they are independent vectors. You can play with them however you want. You get me? So yeah. But result-wise or like effect-wise, yes, they are inversely proportional. You can say that. There's one more thing I wanted to mention about this, by the way. The KVP is exponential. It has an exponential growth. So if you double the KVP, you're going to quadruple the energy of electrons. All right. So if you double it, you're going to quadruple the energy. But when it's an exponential growth or exponential relationship. But with milliamperes, it's a linear relationship. So if you double the MA, you're gonna double the number of electrons. I'm not sure if that's gonna show up on your exam or not, but keep that in mind too. You know, KVP has an exponential growth. So if you double it, you quadruple the energy. But with MA, if you double it, you double the number of electrons. It's a linear relationship. All right. Now we have two types of radiations that come out of the X-ray tube. Now, right now we're still in the X-ray tube, by the way. We're still not talking about the X-rays and how they communicate with the patient. All right, we're still up there in the tube. Now we have two types of energies or two types of X-rays that will come out of the chest of the X-ray tube. You have the general radiation, and you have the characteristic radiation. I'm going to talk about it in a bit, but let's talk about the general radiation, because the general radiation makes up most of the X-rays that come out of the X-ray tube. So most of the X-rays that you get out of the tube are general radiation X-rays, right? And I need you to keep something in mind, that general radiation is bad. They give you bad quality image, they harm the patient, they're useless, all right? All they do is just ruin the picture. Right? So keep that in mind. And we're talking about like 90% of the X-rays that come out of the tube will be in the form of general radiation. So keep that in mind. Now, I doubt they're going to ask you about like detailed physics, you know, like how the electrons interact with the atom. I'm not sure if they're going to do that. I highly doubt it, but I'm going to explain it just for the sake of it, you know, for the sake of completion, I'm just going to do it. Now, yeah, general radiation, it's also called this thing, Google it, I guess. I'm not going to attempt to say it. But basically what happens is that this is the electron that is coming from the cathode. If you remember, guys, the negative cathode is sending electrons to the positive anode. So this is the electron that is coming from the cathode right here. And what happens is that the electron is negatively charged, right? One thing I have to mention, sorry, I forgot to mention that. The anode is usually tungsten. Like the element itself that is used in the anode is tungsten. They asked us about this, so remember it, all right? So the anode is made up of tungsten. And what happens is that the electrons in the general radiation, right? The electrons coming from the cathode will go all the way near the atom, all right? And it's going to change direction. It's going to deflect, all right? It's not going to knock any other electrons out of the tungsten. Like, see those here, this one, it's not going to interact with them, all right? It's not going to touch them. It's going to go to the nucleus, right? And it's going to just just going to change directions, as illustrated here. It's just going to change directions, all right? And I need you to remember something. Energy is not created nor destroyed. So when you let's say you're, I don't know, driving, right? And you're trying to take a right turn. Do you take a right turn? And let's say you're going 60 and you're taking a right turn. Do you take the right turn going 60? You don't. You slow down, right? So you go down to 40. So what happens is basically the same thing. Once it comes close to the nucleus, it's going to slow down just so it can change directions. And this slowing down loses, and so it's losing energy. And just as I said, energy is either converted to something else, right? But it's not created and nor destroyed. Like it's not just going to disappear. It's going to be something, right? And because the electron slowed down, it lost energy. Now, where did this energy go? This energy will be emitted out of the tungsten as X-rays, all right? That's basically what general radiation is, right? You're gonna have an electron, it's gonna get really close to the atom, and then it's gonna change direction. And while changing directions, it's gonna slow down, and by slowing down, it's gonna lose energy. This energy will be converted to X-rays, as you can see right here. This beam thing, that's X-rays, all right? And this is the general radiation. This is the radiation that you don't want. This is a radiation you're trying to decrease. This is what you want to just eliminate, right? But you can't, because it makes up most of the X-rays coming out of the X-ray tube, all right? I hope that was clear. From where is the atom coming? Or where will the atom be? Okay, so the electron itself, this electron right here, right, is coming from the cathode. If we go back here, right here, see the cathode? Actually, let me bring this one up. So the electron is coming from the cathode, this one right here, right? And it's giving you an electron. And this electron will travel to the anode, all right? And the anode is made up of tungsten, just as I said. And you see this atom right here? This is an atom of tungsten. So this is the electron that's coming from the cathode, and this is the atom of the anode, which is tungsten. Is this clear now? Do you get it? All right. Perfect. Do you guys have any questions about this? Can we move on, or I can repeat if you want me to repeat, you know? All right, great. Cool. All right. So we just finished talking about general radiation, right? The bad radiation. Now let's talk about the good radiation, the radiation that actually gives us the image, you know, the radiation that is less harmful to the patient, the image of the radiation that we're trying to increase, right? Which is the characteristic radiation, right? And characteristic radiation, you can see here what's written is like photoelectric effect. We're going to talk about the photoelectric effect later on, because in the body, how the X-rays interact with the, remember, I just said, we're still in the tube. We're still in the X-ray tube. We did not reach the patient yet. But when we do reach the patient, how the X-rays interact with the patient, there are two ways. You have the Compton scatter and you have the photoelectric effect, all right? So just keep that in mind. I'm going to explain them later, but I'm just letting you know what photoelectric effect is, all right? Now, if you guys remember, I mean, obviously you should, it was like 2 minutes ago, I said that the electron does not interact with any other electrons in the tungsten atom, right? It doesn't interact with them. It just goes really close to the atom, to the nucleus, and it changes direction without touching any of the other electrons, okay? Here, it's different. Why is it different? Because you're gonna have the electron coming from the cathode. Normally, you know, like right here, see? It's coming from the cathode, just like in the general radiation. But what happens is this electron is going to go to the inner shell. And let me explain something. You have shells in an atom, you have shells, right? We have one shell here, another shell here, and then you have the outer shell right there, okay? And the further you are from the nucleus, the higher the energy is, all right? So the outer shell has higher energy electrons than the middle shell, and the middle has more energy than the inner shell, all right? So keep that in mind. Now, what happens is that the electron from the cathode, all right, this one, all right, is gonna go all the way to the inner shell. It's not gonna go to the outer or the middle, it's gonna go to the inner shell, and it's gonna knock one of the electrons in the tungsten atom outside. It's just gonna knock it out. Remember how in general it does not interact with any electrons? This one will. This one will knock out one electron, all right? And when it knocks out one electron, what will happen is you're gonna have a vacancy here. This inner shell has one electron less, all right? And it needs to fill it up. Like it has to be filled up. Well, how can it fill it up? It will fill it up by another electron from the middle shell, which is this one right here, is going to come in, all right, and it will go down and replace this electron that was knocked out. All right. So what will happen is, remember that I said that the middle shell has more energy than the inner shell. Now, for an electron in the middle shell, let's say with the energy of 100, whatever 100 is, it's just an imaginary number, right? Keep that in mind. So it's 100, right? To go down, it has to have a lower energy. So it's going to have to be 80 or 60 or 50 or whatever, but it's going to have to lose energy. And when it loses energy, again, same concept. Energy is converted. It's not destroyed and it's not created. So it's converted to something else. So like the 100 that electron had in the middle is going to be 50 because it needs to move to the inner shell. Now you're going to have 50. Where did that 50 go? That 50 will become X-ray. All right. And this time is going to be the characteristic radiation. It's going to be characteristic X-ray, which is good, which we want. All right. So that's basically what the characteristic radiation is. Let me go through it one more time. All right. No problem at all. Now you have an incoming photon, right, or electron or whatever. It's going to knock one of the electrons from the inner shell right here. It's going to knock it out. Okay. It's going to knock it out. And what will happen is an electron from the middle shell will come and replace that one right here. And in that process, is going to lose energy. All right. And when it loses energy, you're going to get emitted X-rays right here. When the electron fills the gap, you get emitted X-rays. And that's basically what characteristic radiations are. You guys have any questions regarding either characteristic radiation or general radiation? What will happen to the electron from the cathode? It's ejected, all right? If you look right here, it's a scattered electron. If you take a look right here, see, it's a scattered electron. It's ejection of the K shell electron. It's just done, right? It's knocked out of the atom shell, right? So nothing really, just becomes useless, really, nothing else. So it doesn't give you, nope, it doesn't give you X-rays. X-rays are not electrons. They are photons, all right? So keep that in mind. Like, you don't get bombarded by electrons, you get bombarded by photons, right? So yeah, that electron is just going to be useless. It's going to be a scattered electron, nothing more, nothing less. And it will also be replaced. Yes, of course, it has to, all right? The only thing that is allowed to have less number of electrons is the outer shell. The outer shell can have a missing electron. And by the way, when that happens, the molecular makeup of the tungsten will change, right? So keep that in mind. Like the tungsten will not be the same after this, right? It's going to be an ion. It's going to change to something else. But the outer shell is the only shell that is allowed to not have the complete set of electrons. Right? It's just going to keep supplying electrons until all the shells inside are full. Is this clear? Yeah. Yep. It all starts inside. All right. So the first shell that is going to release X-ray is the inner shell. All right. And then it's kind of like a chain reaction, kind of. All right. So each time, because if you have more shells, let's say I have 10 shells, this is going to happen 9 times, right? So the inner shell will lose one, and then the number 8 is going to lose one, and then 7 will give it one, and then 6 will give it one, and then 5 will give it one. So it's kind of like a chain reaction, right? It's just electrons are going to keep coming inside. What is the vacuum so that electrons reaches the atom? Doesn't get knocked away. Yep. Yep. That basically, yes. This is in a vacuum, so this electrons reaches the atom and doesn't get knocked away. Let me think about this for a second. Why is it in vacuum? That's a good question. All right, it's in vacuum because of one major thing, all right? If the electrons going from the cathode to the anode are not in vacuum, they're traveling through air. They're traveling through other molecules. They're traveling through vapor. They're traveling through dust. They're traveling through a lot of things, right? So you decrease the amount of electrons that are going from the cathode to the anode. Putting it in vacuum, will ensure that the maximum amount of electrons will reach the anode. Good question. That's a really good question, mashallah. I don't get from where is the radiation coming from. All right. So by radiation, do you mean the X-rays themselves? Is that the question? All right. Let's explain the whole process quickly. All right. I know some people will get bored, but quickly, let's explain it. All right. You have a cathode, you have an anode, right? Cathode will send an electron. This electron will interact with the anode, which is made out of tungsten. All right. And it will give you two types of radiation, general and characteristic. All right. Now, general is bad, harmful. Characteristic is good, gives you good image. All right. Now, in the general, as I said, no electrons are knocked out from the anode, like from the tungsten. It keeps its electrons. All right. What happens is that it's just there's divergence of the electron. So this is the electron coming from the cathode, right? And this is the tungsten atom. This big thing is the tungsten atom. Now, the electron from the cathode does not mess with all the other electrons in the anode. It doesn't come close to them. It doesn't knock them out. It just goes close to the nucleus and it changes direction. That's it. Like the picture right here. See, just changes direction. That's it. And when it changes direction, it loses energy. And this, when it loses energy, it loses the energy in forms of X-ray. So the energy lost because of this change of direction is the general radiation or the general X-rays. All right. And this is what's 90% of the X-rays coming off the chest of the X-ray tube is this kind of X-rays. All right. Now in the characteristics, all right, the electron coming from the anode is so powerful, it will knock out one of the electrons in the tungsten. It will knock it out. All right. And when it's knocked out, another electron is going to come. It's going to replace that knocked out electron inside the shell. And because it's coming down, it's going from the middle to the lower field, it's losing energy. And this energy lost is the characteristic X-rays. This is just a quick summary of both types of radiation, both types of X-rays. Perfect. Any more questions regarding, by the way, this is like the bulk of the lecture because, man, I hate physics. Anyways, any more questions about these two? All right, let's just move on. Again, same thing. But here you need to look at this, all right? So what happens is that this is the general radiation right here, and this is the characteristic radiation right here, all right? I need you to look at this. See, electron comes, does not mess with any of the electrons in the tungsten. It just changes direction. And when it changes direction, it gives you X-rays. That's it, all right? And now one more piece of information that you guys need to know is that general radiation has low energy, right? And low energy is bad. Why? Because low energy is either not going to reach the patient, right? It's just too weak to reach the patient, or if it does reach the patient, it's going to get deposited inside the patient. So the patient will absorb the X-rays, and this is bad because any energy absorbed into the body will cause ionizing damage to the DNA, to the mitochondria, ionizing damage. And that's why general radiation is bad, because it's low in energy, all right? So the lower the energy is, the higher the chance it's going to get deposited inside your body, the more damage it's going to cause, all right? And you can see this by this graph. See how the energy is just super low. And it's also if you notice, it's super scattered, all right? It's super, like it can be anywhere from 10 to 30, all right? It's not fixed, or it's not specific. Let me check the chat real quick. Yes, exactly. Exactly the same. It just can't leave the body because it's not powerful enough, right? So it stays inside your body and it causes damage, and that is bad. You don't want to do that, all right? That's why we try to decrease general radiation, right? Now, compare this to the one under it, or the characteristic radiation, right? Same thing. Electron comes, knocks an electron out, electron replaces it, gives you X-rays. Same thing we discussed, right? But look at this. See? It's very high in energy. It's a very high energy radiation. All right? And this is good because it will penetrate your body. It will go through and through. All right? It will give you the image and leave your body, no harm done. Okay? So that's why characteristic radiation is good. And you wanted more. Okay? Is this part clear? All right. Moving on. Again, same thing. You know, this image is basically those two images just combined, you know, superimposed on each other. You can see both of them. You can see the general radiation down right here. And then you can see those spikes. Those are the characteristic radiations. No, same thing, I guess. Yeah. Again, this just shows you that this is the characteristic radiation and this is the general radiation. Nothing more. Okay, so as I said, the X-rays are either absorbed or scattered, and or they can be just, you know, they can penetrate the body. All right, filter. What's a filter? A filter is something that you place between the X-ray tube and the patient. All right, so before the X-rays reach the patient, you make them go through a filter. And what does this filter do? Yes, they happen at the same time. As I said, you have 100% X-rays coming out of the tube. 90% of them are going to be general radiation or general X-rays, and 10% are going to be characteristic radiation or characteristic X-rays. All right, but both of them are happening at the same time. All right, because think about it: the chances that this electron is going to hit this electron and then it's going to knock it out, and then another electron is going to come and substitute for it. The chance of this happening is way less than the general radiation, where it just goes and just changes direction, you know. So the chances that an electron is going to hit another electron, and then, you get the point. So it's 90% general and 10% characteristic, but they are happening at the same time. How do they scatter? What do you mean? How do they scatter? What do you mean by scatter? Because I didn't explain scatter yet. So earlier slides. Okay, so yeah, got you. All right. See this one? This electron right here, the electron that got knocked out. That's just, you know, the electron from the cathode that came and then knocked the electron out. This electron that got knocked out, this is what we call scattered electrons. All right, it's just scattered, no use. Nope. Yeah, the electron itself. All right, it's just useless. Right, but I'm gonna talk about. So I'm gonna talk about scatter in relationship to X-rays later in the slide, because there's X-ray scatter too. Right. Even though capture the image. Yes. Yeah. 10% is characteristic, and 10% is what we try to increase, because characteristic is the one responsible for the good quality image and the least harm done to the patient. So you try to increase that. I'm going to show you guys how to increase characteristic radiation later on. But yes, it's only 10%. Generally speaking, in normal X-rays, 10% is the average of the characteristic radiation that you get. All right. You're welcome. All right, so for a filter, right, as I said, you have the X-ray tube. It's giving you 100% X-rays, right? 90% of them are general X-rays, and 10% of them are characteristic radiation or characteristic X-ray. Now, before those X-rays reach the patient, you make them go through a filter, all right? And they asked us about this. I'm not sure if they're going to ask you, but remember it. The filter is usually aluminum, right? So you have tungsten in the anode, and you have aluminum, a sheet of aluminum as the filter, okay? So what happens is that any radiation that is low in energy, and if you guys recall, low energy, which type of X-rays are low in energy? The general radiation, the bad ones. Exactly, guys. The general ones are low in energy, and you want to eliminate them. So what will happen is that the ones that are weak, the ones that are low in energy, are not going to be able to make it past the filter. All right. So this is one way you can increase the amount of characteristic radiation. You can increase the amount of characteristic radiation by decreasing the amount of general radiation. All right. So this is one way you can do it, by putting an aluminum sheet or an aluminum barrier between the X-ray tube and the patient. All right, it's pretty simple, really. It's just straightforward. Anything that's not strong enough, it's just not going to make it. All right, so keep that in mind. This is just a demonstration. Just see, you have here the aluminum filter right here. This is the tube, the X-ray tube. I don't know why I keep saying chest tube. This is the X-ray tube, right? And this is the patient, should be here, right? Like, should be here, right? And then you have the aluminum filter right here, okay? Actually, let me talk about this too here. You have this here, which is called I don't know how to say it, all right? But you guys figure it out. This thing right here. What happens is, it's gonna let all the X-rays, right, go through this small slit, all right? Why? Because if it makes it go through a small slit, the scatter later on is going to be decreased. All right. So the smaller the slit is, the basically that's perfect. Yes, it just concentrates them. So instead of all the X-rays going right and left and in a wider angle, it just decreases this angle, so it's more focused on the patient, right? You don't want all those X-rays just going away. You want them on the patient, right? So this is basically what this lead coal. I don't know how to say it, but you guys get it, you know. Again, filter more. This just tells you that the object flips. So like, if you look on an X-ray, right, it's not going to be your right hand to the right side of the patient. No, it's going to be your right hand to the right side of the patient. It's the other side, you know. It's just the anatomic position, you know. I hope this point is clear. Like, you don't get a straight image. You get a reflection, right? So your right is their left, and your left is their right. That's basically it, Jamie. All right. Now we talked about the X-rays in the X-ray tube, right? Now let's move on and see how the X-rays coming from the tube interact with the soft tissue or the tissue of the patient. How do those X-rays interact with the patient himself or herself, right? Now you have two major ways of interaction this happens. You have the Compton scatter and you have the photoelectric effect. All right. Now the Compton scatter is bad. Compton scatter is what you think of when you think of general radiation. So general radiation gives you Compton scatter. That's bad. That's horrible. You don't want general radiation and you don't want Compton scatter. You want to reduce both of them. All right. And if you guys recall, the characteristic radiation will give you the photoelectric effect. You want to increase photoelectric effect. You want to increase the characteristic radiation, because these two are good. All right. They give you good quality. They have the least amount of harm on the patient. Okay. Then you have elastic recoil and pair production. Those two are absolutely useless, right? They don't do anything at all. But yeah. All right. Let's talk about them in details. All right. So the Compton scatter is that unbound electrons in object energy for higher than the confinement leads the atom to lose an electron. also called ionization. All right. Now, do you guys remember how I said in the characteristic radiation, one of the electrons is ejected, right? This happens in the X-ray tube. In the body, all right, the general radiation will lead to or will knock out one electron in the human body, all right? So your atoms will lose electrons, or they will get ejected because of the Compton scatter, which is bad. Because when you lose electrons as humans, right, this is damage to us. This is what we call ionizing damage. You lose electrons, you alter your DNA, higher chances of cancer, higher chances of necrosis, stuff like this. In a sense, yes, that's how reactive oxygen species are made, but you don't get ROS by this, right? You get direct cellular damage. You get direct damage to your DNA using the Compton scatter. But in theory, they are the same, right? It's just different causes. Here, the cause is X-rays. The other thing, the other way is the excess oxygen, all right? But basically, in theory, they are the same, right? So what happens is that, can you keep this slide like really? Yeah, sure. Yeah, of course. All right. So here, this is the Compton scatter, right? And I said that the Compton scatter equates to the general radiation, right? And if you remember, general radiation, they don't knock or they don't mess with the electrons in the tungsten. No electrons are being knocked out, all right? So what happens is, in the chest, in the X-ray tube, the general radiation will not mess with any electrons. But when they reach the human body, they will knock electrons out of the atoms in your body. And this is bad. You don't want that to happen, but it does. But you get the point? Like fog in the X-ray tube, no electrons knocked out. But in your body, electrons will be knocked out by the general radiation. All right. So basically, it's all right. You got it, bro. All right. This is basically, again, the Compton scatter. Remember what I said, X-rays are photons, they are not electrons, right? So what you see here is that you have an incoming high energy photon, all right? Or a photon, basically, all right? And what happens is, this photon is gonna knock one of the outer shell electrons, all right? So there will be no substitutions, there will be no electrons substituted for other electrons, no. The electron that was lost is in the outer shell, so there will be no any replacement. Okay, so keep that in mind. But what happens is this photon, right, is stronger than the electron. So it has a higher charge than the electron in the outer shell. So this photon right here is higher in energy than the electron that's right here. So what will happen is this photon will come to do two things. It will knock out one electron, just straight out, knock it out, right? And then it will basically just bounce, right? So it will hit the electron, knock it out, and then it will bounce. But this bouncing, right, it's going to be lower in energy because it wasted energy trying to knock that electron out. So it had 100, and this electron is 50, right? The photon has 100. It will come, it will waste 50 on this electron to knock it out, and then it will bounce out, right, as a lower energy photon. It will be 50 because it wasted 50 on the electron. I said 50 a lot. I'm not sure if you guys are still with me. Are we good? Are we bad? It goes to damage others. Yeah, basically it goes to damage other parts of your body, right? It sometimes goes and it disrupts the image made by the characteristic radiation. So the characteristic radiation are good. They will go and they will do the photoelectric effect and they will give you a beautiful image. But the scattered low energy photons, those are just going to interrupt them, right? So they will make your image worse. So not only do they damage you, they make they just bad. That's all I gotta say. They're bad, bro. I don't know what to say. You get me? So that's basically what the content effect is. What are E1 and E2? Where's E1 and E2? Do we have an E1 and E2 here? Can't see E1 and E2. Oh, okay. It's basically telling you, it's labeling the photon as E1, and it's labeling the outer shell electron as E2. So it's basically telling you that E1, which is the photon, has a higher energy than the electron. And that's how it's able to knock it out and then bounce and still be there, but in a lower energy form. What is energy? What is the energy incoming photon? Yes, E1 is the energy incoming photon. Is it? E2 is the electron in the outer shell. But also, by the way, by your definition, it's true. E1, which is the photon before it hits the electron, is higher in energy than E2, which is the photon after hitting the electron. So this photon right here is higher in energy than this photon right here. All right. So by your definition, it's also true. You're not wrong. All right. Any solutions to solve this? I'm going to talk about it now. And the way you can do this, they are not the same. No, they're not the same. And the way you can do this, the way you can prevent or decrease the content effect is by manipulating the milliampere and the kV that we mentioned at the beginning of the lecture. And I'm going to talk about this later when we talk more about mammographies and stuff. All right. Again, see, I just mentioned it, man. You got the KVP. If you increase the KVP, you increase the content effect, you decrease the image quality. All right. So you guys remember what I said? KVP increases the energy of the electrons. And when you increase the energy of electrons, the content effect increases. And this decreases the image quality, right? So if you go right here, content scatter dominates in higher energy rays, all right? So if you increase the energy, you increase the content scatter, you decrease your quality, the quality of your image. All right? Okay. But are in general rays low energy? Yes, they are. They are low energy. Well, let me explain this. How can I explain it? It's kind of hot. We'll come back to this. All right. We'll come back to it, but let's just talk about photoelectric effect first. You're welcome. The most important interaction with the object, energy of photon is much higher than the E-binding energy. Energy is absorbed. All right. So, have you guys seen a mammography before? Basically, a mammography is a very high quality X-ray, right? And we get it because we're not trying to visualize bones, we're trying to visualize soft tissue. And this is one of the few times you actually try to visualize soft tissue on an X-ray using a mammography, right? And how do they do that? They do that by decreasing the KVP, so that when you decrease the KVP, you do two things. You decrease the content scatter and you increase the photoelectric effect, all right? So what happens is that the energy of the photon, all right, that is coming is much higher than the E-binding energy. Let me show you. All right, there we go. All right, so you have, this is the photoelectric effect. You have the photon coming, all right, and what will happen is that this photon will interact with an inner shield electron, just like in the X-ray tube, right? Just like in the X-ray tube. What will happen is that it's going to go and it's going to interact. All right. You have KVP and you have milliampere, right? KVP, when it's increased, you increase the content scatter. And when you increase the content scatter, you decrease the quality of the image, all right? you're trying to decrease Compton scatter as much as possible, all right? But what happens is there's a certain limit, is that when you decrease KVP too much, your image gets really dark and you can't see anything. So there's a limit on how you can decrease the KVP. But basically, when you increase KVP, you increase the Compton scatter, you increase the energy, and you decrease the image quality. And the opposite is true. All right. When you decrease KVP, you decrease Compton scatter, and you improve your quality of the quality of your image. All right. And I'm going to talk about milliamperes too, because milliamperes plays a role in this. All right. So for the photoelectric effect, you have a photon coming from the X-ray tube. All right. But this time it's interacting with an inner shield electron. It's not interacting with an outer shield electron. You remember in the Compton scatter? In the Compton scatter, it's interacting with one of the outer shield electrons. All right. So when you go down here, it's interacting with an inner shield electron. All right. And it will knock it out, right? Just like in the Compton scatter, all right? It will knock it out. But this time, because it's an inner shield, what will happen is electrons from outer shields will come and replace it, right? It's going to go down from the middle shield, and it's going to go down right here to replace the knocked out electron. And just like with the characteristic radiation, when an electron goes from a middle shield to a lower shield, it loses energy, and it loses those energy in the form of what? In the form of X-rays. And those are the X-rays that penetrate the body, all right? So it won't stay in your body, all right? It's not a photon anymore, right? Like, khalas, it's gonna penetrate your body. It's gonna go through and through. I think I have a, yeah. No. Take a 5-minute break. Can we take a, how many slides do we have left? I have 15 slides left. Yeah, we can take a 15-minute break. You can take a 15-minute break. Let me just answer those questions, and then we can take a break. Photoelectric effect is mediated by who? A characteristic radiation, right? Always try to correlate them, right? Although there's like overlap between them, between characteristic radiation and general radiation, they overlap when they cause the photoelectric effect and the Compton scatter. But generally speaking, general radiation, Compton scatter, characteristic radiation, photoelectric effect. All right. Let's take a 5-minute break. Cool. And we're going to finish this, inshallah. What's the reason I hate physics, man? Some things doesn't make sense. Just got to memorize it. Anyways, let's put this on. All right. So those are the two things I was talking about, the elastic scatter and where's the other one? Oh, the elastic scatter and the other one, the useless ones, you know, the ones that you really don't need to know, but, you know, just keep them in mind. They don't do anything really, right? They're 10% of the interaction with the object. So like after X-rays interact with the body, what's released from the body, 10% of it is the elastic scatter, right? And basically nothing happens. The photon or the electron, the photon coming from the X-ray will just bounce off. You said the X-ray coming. The X-rays coming from the characteristic radiation is not that harmful because it's not a photon anymore. No, it is a photon. It's not an electron anymore. You know, it's not an electron. It's a photon now, right? Because X-rays are photons. Keep that in mind. There is no electrons in X-rays, right? Like electrons is what gives you photons, right? So keep that in mind. X-rays are photons. No electrons involved. All right. You're welcome. It's just how they interact with the body, right? How they interact with the body is what makes the difference, right? When you knock an electron in the outer shield, that is bad. because it changes the molecular makeup of the body, right? It leads to DNA damage, it leads to direct cell death, right? So keep that in mind. It's just how they interact with the atoms in your body is what differentiates them. Cool, but they are still photons, they're not electrons. Now, in the elastic scatter, which is the third type, what happens is that the photon coming from the X-rays will have an equal energy of the electrons in your body. So what will happen? It's just bounce off. Nothing will change. All right. So it doesn't contribute anything to the image formation. Right? It doesn't, because when it interacts with your body, the photon that results is different in energy. Right? It's going to be lower in energy. All right. And this is what changes the X-ray film or the X-ray sheet. Right? But if it just bounces off without changing energy or changing states, it's not going to cause anything. It's not going to distort your image. It's not going to make it better. It's not going to affect you because you didn't change the structure of the atoms in the body. Cool. That's basically what elastic scatter is. It's just, remember, E1 is equal to E2. Nothing different. All right. So now this is how the X-ray images are formed, right? So you see B1, B2, T1, T2, T3, and air basically tells you how they will appear on the X-ray film or the X-ray sheet, right? And the denser the structure in your body, the brighter it is, it's going to be on the X-ray sheet or the X-ray film. So if you look at B2, although it doesn't say it, but B2 is probably what? Denser, wider. So what's B2? What's this right here? What's B2? No answers. Okay. Yeah, B2 is bone.
Is it
basically?
Bone?
B2 is bone. Yes, you're right. B2 is bone. So because it's the densest thing in your body, it's gonna appear the whitest. Let's just gonna be plain white. Okay. So that's basically what the slides tell you, that bone will appear white, and because air is not dense at all, it will appear black. And when you look at that chest X-ray, what appears black? Like when you look at it, what organ is black? Your lungs. Perfect. Why? Because it's filled with air. Okay. So that's basically what this really tells you. Yeah. Again, same thing, really. Nothing to explain here. Okay. So remember the slit I was talking about, right? It's just use, decrease, scatter, right? Because what happens is scatter is the X-rays going right and left, up and down. It's just, being chaotic basically. And you decrease that by making the X-rays go through this narrow slit in your X-ray machine. And what happens when you decrease scatter is that you decrease the dose, all right? And you increase the image quality. Why? Because scatter itself, it increases the dose of radiation that the patient receives, and it decreases the image quality. So you decrease scatter, that's good. How do you decrease scatter? Using this slit thingy, all right? That's basically what scatter does, right? Decrease scatter, improve image quality, decrease the amount of radiation that the patient receives. Grids never came up. How does it decreases the radiation? Doesn't decrease the radiation, it decreases the dose of radiation, right? So like it's gonna be the same amount of radiation, but instead of, so let's say you're taking a chest X-ray, right? Let's say you're taking a chest X-ray. The image will give you a chest X-ray, right? But because it's because the film was on your chest, right? The film, the X-ray film was behind your chest only. Cool. But the X-rays coming in front of you, right? They are going and they're hitting your head, they're hitting your abdomen, they're hitting your legs, because you're not decreasing the scatter. They're just scattering everywhere, right? You're focusing them on the chest and only the chest. And that's how you increase the image quality, right? And that's how you decrease the amount of X-rays going to other parts of your body, right? So you don't want X-rays going to your head. You don't want X-rays going to your legs, right? You just want them on your chest. And that's how you do it. You decrease scatter, you're welcome. You improve quality, you decrease the dose. Grids, the teacher didn't explain it. The professor didn't explain it to us in our batch. The professor didn't explain it to any of the previous batches. And honestly, I didn't bother researching it. Did the professor talk about this to you guys? Because if the professor did, in tomorrow's session, inshallah, I'll just go. I'll just explain it real quick. Yes or no? Did the professor explain this? I think she skipped the slide. Yeah, she did. She did with the previous batches too. So I would be surprised if she explained it to you guys. Again, grids. All right. We can check and confirm. Yes, please do that, and just let one of the G&D guys let me know. And if she did explain it, I'll just explain it tomorrow, inshallah, in tomorrow's session. Cool. Come on. So this slide is about the air gap, right? So what's an air gap? You have the X-ray machine right here, and the red circle is the patient, right? What happened? Basically, she explained the second slide of grid. Okay. I'll research it, right? I'll see what the grid is, and I'll let you guys know tomorrow, inshallah. Now, for the air gap, let's talk about the air gap. The air gap is another way of decreasing scatter. Okay, so the closer the sheet or the film of X-ray is to the patient, the less the scatter is. All right. So see, the air gap is basically the gap between the receptor right here and the patient. Cool. Now, if you increase this gap, you allow for the X-rays to scatter more. All right. And this doesn't have anything to do with the dosage, sure, but it does have to do with the image quality. All right. Now, if you have, let's say, 100% of the X-rays are going through the chest, all right, and they're going to the back, right? They're exiting your back, right? You want to catch them as soon as they exit your back. As soon as they exit your chest, you want to catch them على طول. Why? Because if you leave a gap between the patient and the sheet, some of those X-rays are gonna bounce too wide, and they're gonna miss the sheet, or they're gonna miss the X-ray film, right? So basically, what this slide tells you, the more you decrease the air gap, the better your image quality is, because you're catching all of the X-rays. If that makes sense. Does that make sense? Perfect. All right. All right. So for the image quality, you have basically 3 types of resolutions, or 3 types of ways you can evaluate the image quality. You have a spatial resolution, you have the contrast resolution, and you have the temporal resolution. Now, temporal resolution are not really that important when it comes to plain X-rays. They are more important in fluoroscopies or like live X-rays, where you can see what's going on inside the patient's body while doing the X-ray. Then why don't we stick the receptor to the patient? Why leave a gap? Honestly, I don't know. I'm not really sure, but like, I mean, I think that's the whole point. You know, you don't leave a gap. That's the whole thing. That's the whole point. I think that's how they do it, because I remember having a chest X-ray before, and I was like, you know, touching the receptor or touching the X-ray film. So I think that's what they actually do. They don't allow for space between the patient and the receptor. It's just, you're always close. I don't know if you guys had an X-ray before, but I always had like something like really close to my back, and I think that was the receptor. So yeah. All right, so for spatial resolution, contrast resolution, and temporal resolution, as I said, the temporal resolution is more important in fluoroscopies, and like, you know, guys, you know, the barium swallow tests, you know, where you want to visualize the patient as the patient is swallowing a contrast, you know. Sure. Okay, so you have X-rays coming right here, right? This is the X-ray machine, this is the patient in red, and you have X-rays going through the patient, right? Now, right here, you have your image. This is the image you want to get. And between those 2 lines, once they exit the patient, those are the X-rays you want to catch, or you want to visualize on the sheet or on the film of the X-ray. Cool. Now, I'm not sure, Ismail, if it has anything to do with the dose, because it already exited the patient, it already left the patient body. So I don't think it has to do anything with the dose. It has to do, what I'm sure of, is that it has to do with the image quality itself. Done? So back to this, if you see though between those two lines, once they exit the patient's body, you want to catch those on the film, right? Why? Because this is the image, right? This is the image that's coming out of the patient. You want to catch it as soon as it's out. Because if you give a gap or you leave a gap between the receptor, right, and the patient, the X-rays coming out of the patient's body will scatter. They will just keep on going right and left, and they will miss the receptor. So if you put the receptor all the way back here, can you see it right here, the black line? If you put it all the way here, you're missing out on all of these. See all of these? Gone. These are X-rays that could have been useful in making the image look better, but you missed them. Why? Because you put the receptor like far away from the patient's back, right? But if you move the receptor and it's right behind the patient, all those X-rays exiting the patient will be displayed on the film. So you're not missing out on anything. All the resolution or the quality, all the X-rays are hitting that film or hitting that sheet of X-ray, right? So nothing is scattering away. Nothing is missing the film. But if you put it behind, things are gonna miss the X-ray sheet. Is this clear? Welcome. All right. So let's talk about spatial. Do you guys know, okay, back to this again. Do you guys know what the fluoroscopy is or barium swallow test is? Okay, great. It's basically this, that this is what temporal resolution is that it's beneficial when you're doing a fluoroscopy or when you want to get live pictures of something moving throughout the body using X-rays, all right? This is when temporal resolution is important, right? Now let's talk about spatial and contrast resolution first. Yeah, basically your esophagus, your GIT, basically whatever it is, but you want to visualize it live as it's happening right now. You don't want a picture, you want a video, all right? That's when temporal resolution is important. Now let's talk about spatial resolution. And now spatial resolution is basically the ability to distinguish two adjacent lines. Now, a better way of saying this is that it's the number of pixels, right? Just remember it like this. It's the number of pixels in the image, right? Now let me explain this. I need a pen. All right. Now, if you have this is a line, right? Let's say this is a line. Can I change the color? Yeah. And this is another line, all right? And this is another line right here. Okay? You have three lines, three different colors, all right? And you want to detect each one on its own so that you can differentiate between them, all right? So you want to, because let's say you're looking at the lungs. Most of the lung is black, but you have a vessel. You have a pulmonary artery branch. You have a terminal bronchus, all right? Those will have different colors, right, than the lung. The lung is going to be black and the bronchus is going to be white, right? And you want to differentiate between these two. You want to see the difference between the white and the black, because it's going to tell you that the white is the bronchus and the black is the lung. So you want to see that. Now, how do you do that, right? Think of pixels, right? If you have, let's choose another color. Let's choose black, or not white for sure. Where's black? Black, right? If you have a small, pixel, right? Let's put a pixel right here, and then another pixel right next to it, and then another pixel right next to it, right? You have three pixels, they're small, right? Each pixel is gonna give you a color, right? Because this pixel is on the red, it's gonna show you red. This pixel is gonna be red. The pixel next to it is gonna be orange. The pixel next to it is gonna be green, right? So you can differentiate between red, orange, and green, right? So basically, the smaller the pixel is, the more lines you can distinguish between. Now, think of it like this. What if we put a huge ass pixel right here? Pixels don't show different colors at the same time. One pixel will show you one color. So if you have a big ass pixel right here, it's just gonna show you one color, either red or all orange or all green. This is going to be one color only, and you're not going to be able to differentiate between those three lines because the pixel is big, right? But if it's small, you have three of them next to each other, you're going to be able to tell that this is red, orange, and green. All right, and basically this is what spatial resolution is. The smaller the pixels, the more number of pixels you have, the better the spatial resolution of a picture is, the better you can differentiate between two lines or lines in general. The bigger the pixel, the more lines are going to be incorporated in each pixel, the less you can distinguish between lines. Did that make sense? Yes, no? Perfect. Any questions about spatial resolution? All right, most of you guys look like you're clear on this. Guys, please, I am begging you, if you have any questions, let me know. All right, let's not move past something without understanding it, because it's going to be a chain reaction. You're not going to understand this point, you're not going to understand the next point, you're not going to understand that. All right, so if you have any questions, let me know. Cool. All right, now let's talk about contrast resolution. All right, and what is contrast? It's easy. Let's say you have black and you have white, right? Look at the image on the right. It's black and white. There's nothing else. It's just black and white. And you can't differentiate between everything else in between. From the picture on the right, you can tell that you can see bones and you can see lung. What else can you see? Nothing. Why? Because other organs have different attenuations, or they absorb a different amount of X-rays, right? So you want to have everything in between black and in between white, right? So you want the shades of gray to be there. And the more shades of gray you have, the more you can distinguish between different structures. So one bronchus can be thicker than the other bronchus. Bronchus A can be thick, bronchus B can be thinner than bronchus A. So they will appear differently and they will have different shades of gray. So the more shades of gray you include, the better your contrast resolution is, right? So if you can, for example, here you have only black and white on the right, but on the left you have black, 50 shades of gray, white. And that's how you can differentiate between them, or like between structures, or between, did I say 50 shades of gray? Yeah. Yeah, that's how you can differentiate between structures. Did contrast resolution make sense? Did this explanation make sense? All right. Cool. Nice. All right, now we're talking about the temporal resolution, right? And temporal resolution, as it says, is the ability to capture moving objects at different points in time. And this is measured in frames per second. Now, do you guys know when you play, I'm not sure if all of you play video games, but like FPS or frames per second, the more FPS you have, the smoother the video is, the better the video is, So a video or a video game that's playing on a 240 FPS, you feel like it's real, you feel like it's way smoother than 60 frames per second, right? Because what are videos? Videos are pictures, right? Displayed back to back to back to back, right? So the more pictures you have per second, the smoother it is, the smoother the transition is, the smoother the video is, the more clear it is. So the higher frames per second you have, the better your temporal resolution is. We're good. And it says here it's like moving structures like barium swallow and coronary angiography. Yeah, that's basically what it is. Perfect. This is a fluoroscopy. You guys can Google it or like put it on YouTube. It's nothing amazing, but yeah, that's what a fluoroscopy is. You guys know what this is? What's this structure? It is the esophagus, yeah. And what's inside the esophagus? What is this white thing? Barium, perfect, yeah. And why is the esophagus looking like this? Like, why is this part looks great and smooth and hollow, but this part doesn't? See, this is the lower esophageal sphincter right here. This is the LES. We're talking about like something in the mid esophagus right here. Why does it look like this? Barrett's esophagus actually is not cancer, so it can't cause filling defects when you're, because this is what we call a filling defect. There's something right here that is not allowing, yeah, stenosis or obstruction. This could be cancer, or it could be an esophageal stricture, all right? So could be compression from outside. It could be, but then this is going to be smoother. Can you see like the inside of the esophagus is going to be smooth, right? It's not going to be bumpy, lumpy as it's right here. This indicates like there's something inside the esophagus. Either there's like fibrosis in a stricture, or there could be a cancer, could be an esophageal ring or web or whatever, right? So this is not part of the lecture, by the way. I just like to, you know, make it more clinical because I'm more interested in the clinical aspect of radiology than this. But yeah, good job, guys. Stenosis, obstruction, all works. But this is not Barrett's esophagus, though. All right. Mammography. Remember, guys, what I said about KVP? If you increase KVP, you increase what? Yalla, I'm gonna test you. I don't care. Yes, you increase the Compton scatter. When you increase Compton scatter is bad. It's gonna decrease the image quality, right? So what you do with a mammography is, because a mammography is a more specialized type of X-ray. It's an X-ray that you're trying to like detect soft tissue, microcalcifications, stuff that are very, very, very hard to detect on X-rays, right? So you want to increase the quality as much as you can. And that's what we do in mammography, right? You decrease the KVP, usually less than 35. I'm not sure if you should remember numbers, to be honest, or not. Like I don't know. If you want to memorize it, be my guess. But you decrease the KVP as much as you can without compromising the image, obviously. But you decrease the KVP so that you decrease the Compton scatter, so you get a better quality image. So you can detect the small things like the microcalcifications and the masses in the breast, right? Also, they changed the anode tube. Remember what I said? In a general X-ray, the anode is tungsten. Here it's molybdenum. I don't know, bro. Google it, I guess. All right. So that's basically what they do in mammography, right? You get a high spatial resolution. All right. One more thing. Remember the slit I talked about? In mammographies, it's 0.3 millimeters. When you compare it to a normal X-ray, it's from 1 to 3 millimeters. All right. So remember, you decrease the slit, you decrease scatter, you improve the quality of the image. Right? So mammography improves the quality of image using two ways. It decreases KVP, so it decreases Compton scatter, so it improves the image quality. It also decreases the focal point or the focus point of that slit to 0.3 millimeters instead of 1 or 2 or 3 millimeters. Right? That's basically how mammography gives you a better image quality. Is this part clear? Perfect. All right. This is a mammography. The arrow is showing you a microcalcification. Yeah. Radiation dose control. Okay. Remember, guys, what I told you? How KVP is exponential in nature and milliamperes are linear in relationship. So when you increase KVP, when you double KVP, you quadruple the energy of the electrons, right? You remember that. It's the same concept. If you decrease KVP by half, you quadruple the decrease in energy, right? And this is the same thing when you're talking about milliamperes. Now, milliamperes is a linear relationship. It's not an exponential relationship. So if you decrease the milliamperes by half, you decrease the number of electrons by half. This reduces scatter and wait, reduce scatter or yeah. Oh, okay. So another way, so to decrease the dose, you can decrease the KVP, you can decrease the milliampere, all right? Or you can reduce scatter by using the filters. Remember the aluminum filter I talked about? You can use that too to decrease the dose, or you can decrease the air gap, which is already decreased. I'm not sure why this is mentioned, like common sense to put the X-ray film right behind the patient. I'm not sure why this was mentioned, but like, yeah. Are we good, guys? Perfect. Oh, we're done with the lecture. Okay. This card. Oh, I don't care. Okay, let's talk about. Let me open the lecture and I'll answer your questions right now. Okay, let's see the questions. How does the gap contribute to radiation? Also, what about pair production? Where are we increasing the electrons? شوفي Fatima, anything coming from the X-ray is harmful. All right, it's just the difference of harmfulness in the X-rays, right? So anything that goes through your body will be harmful. It's just how it's a matter of which is more harmful to you, right? So if you decrease milliampere, you're decreasing the dose, which is good. You want that. Even if it gives a better image, right? Yes, yeah. You decrease that. You're welcome. How does the gap contribute to radiation? Also, what about pair? Okay, I don't know what pair production is, so you're gonna have to explain that to me. But how does the gap contribute to radiation? That's a good question. I'm not sure it does actually. I'm gonna have to read more about the grid thingy, and I'm gonna come back to you about how the gap correlates the amount of radiation. All right. Cool. Now let's talk about contrast material. Honestly, this lecture is just filled with things that you just gotta memorize. There's not much to remember, to like understand. There's not much of explaining to do, but I'll go through it either ways. I hope you guys know what contrast is. It's all about contrast. Okay. Okay. So we basically give contrast to give, like we give contrast material to improve the contrast resolution. You remember the contrast resolution I talked about? So when there's two shades of gray, right, next to each other, it's sometimes hard to distinguish between them. So what you do is you give something that is contrasting in color, something that absolutely looks different, all right, so that you can see those two better. Does that make sense? I'm not sure if that makes sense, honestly. All right, cool. All right, I'm glad it makes sense. So basically you want something to compare it to that is drastically different so that you can see the similarities between the two that you're not really appreciating right now. Okay. So it depends on the mass density. Mass density is what I talked about in your body. You see how your bone has a different density, your lungs have different density, your heart has a different density. That's basically what mass density is. All right. And if you look at this now, see how there's different mass densities here. You see, like, look at bone. Bone is 1.85 mass density. Muscles is 1. Fat is 0.91. Lungs is 0.32. Air will probably be less. It probably will be something like 0.02 or something, you know? So the denser it is, the higher your mass density is, obviously. But now compare those numbers to the contrast material. Look at this. You have barium, which is 3.5. Iodine, which is 4.93. And then you have air right here. See, it's really low. Okay. So that's just telling you how the mass density of contrast is way higher than most things in your body. Actually, all things in your body. Nothing has a density of 3.5 in your body. All right. And that's what gives them this startling resolution on imaging. All right. You like, they are so white on imaging. All right. It's called differential absorption. Differential absorption is just basically how the heart absorbs the X-rays differently from the lungs, differently from the bones, differently from the contrast. Nothing really here to explain. All right. So to prepare the patient has to be NPO. What does NPO is? What does NPO mean? NPO means nothing per mouth. Right? So the patient has to be fasting for at least 6 hours prior to the procedure. All right. But this is only for general anesthesia patients. So if you're going under general anesthesia, you have to be NPO for at least 6 hours. Right? But if you're a non-general anesthesia patient, you can just follow the protocol of the hospital. But basically, it doesn't require fasting. You need fasting if you're going under general anesthesia to prevent. What do you want to prevent by going NPO and the patient is going under GA? What do you want to prevent? Why are you making the patient fast? Vomiting, yeah, aspiration. You don't want the patient to vomit or aspire and like the GI content going back and entering the lungs, right? So basically you want to prevent aspiration. Obviously with the patient's weight different, like the different weights require different amounts of contrast. The bigger the patient, the more contrast you're going to need to use. Now in asthma, there's no really any contraindications. Patient can have asthma and can undergo contrast material without having any prophylactic procedures or medications administered. All right. If the patient is in an asthma CT, so someone taking a CT before surgery. Taking a CT before surgery, you'll probably be MPO because of the surgery, not because of the CT, right? But someone who needs imaging using contrast and they need to be under general anesthesia are patients, for example, it's not kids, right? Because if you move inside a CT scan or an MRI machine, the image will be distorted. So you need the patient to be very still. So when it comes to children, we sometimes place them under anesthesia, right? So these patients have to be NPO. You're welcome. So in asthma patients, as I said, if the patient has a history of asthma, there's no contraindications. There's no medications to give this patient. They can just undergo the contrast infusion, no problem. But if the patient is in an acute exacerbation, like the patient is dyspneic, he can't breathe, he's gasping for air. All right, NPO is nothing per oral. So NPO, nothing per oral. So the patient is not ingesting anything using the oral route. So no drinking and no eating, right? Basically, the patient is fasting from anything that's ingested through the mouth. And you do that because if the patient goes under general anesthesia, they lose all control. And sometimes the GI content, the content in your stomach, can go and reflux back up. And the patient won't vomit. The patient will aspirate. So instead of going outside and vomiting, the patient will have all this GI content enter the lungs. And this can cause aspiration pneumonia and aspiration pneumonitis. And those could be really bad. All right. So that's basically what NPO is. Now, back to asthma. If the patient is in an acute asthma exacerbation, you don't give the patient any IV contrast. You send them back to their primary physician, right? Deal with the asthma exacerbation, then send him back to me or send her back to me, right? Now, if the patient has a history of an exacerbation in the last 48 hours, this depends on the radiologist's preference. Some radiologists will be, okay, whatever, I'll do the contrast, some won't. So it really depends on the radiologist's decision, right? But there's no protocol for this. For allergies, you need to ask the patient about any allergies before giving contrast, especially because one of the most important complications of contrast is allergic reactions. So you need to ask before administering anything. And by the way, generally speaking, we don't really give those patients anything, all right? But we become on high alert, right? So what happens is you're not going to give this patient anything, all right? That's the general rule, but sometimes you do give them prednisone or diphenhydramine, right? But basically they don't need prophylaxis always, but we become on high alert. So there will be a crash cart. They're going to be the code blue team standby, just in case anything happens. Now for diabetic patients, right? The problem with diabetic patients is that they use the drug metformin, right? And the drug metformin has been associated with lactic acidosis, which could be fatal. Now, only patients with kidney disease who are taking metformin can develop lactic acidosis. So if you have only diabetes and you're normal, you don't have any problems with your kidney, metformin is not going to cause lactic acidosis. But if you are diabetic and you do have kidney injury or chronic kidney disease, metformin can lead to lactic acidosis in those patients. So because IV contrast is also excreted through the kidney, you're putting even more burden on the kidneys now, all right? The metformin and the IV contrast, all right? So what will happen is if the patient has an eGFR more than 30, there's no need to discontinue metformin, all right? You can keep giving the patient metformin and give him or her the oral contrast or the IV contrast, no problem, right? But if the GFR is less than 30, you need to discontinue the metformin temporarily before the procedure and up to 48 hours after the procedure. When can you give the patient metformin again? Once the renal function has been evaluated or you've done renal function testing on the patient, all right? So remember the cutoff number, which is 30, all right? If it's more than 30, give the patient metformin, give the patient IV contrast, you're good. But if it's less than 30, discontinue it before and up to 48 hours after the administration of the IV contrast. Are we good up until now? Are we good with asthma, allergies, and diabetes? Okay. So, now, in any procedures that requires contrast, you have to get renal function testing. Which the slide behind the diabetic patients, or the takeaway is 30 mLs per minute is the cutoff point of when do you stop metformin and when do you not stop metformin. If it's more than 30, don't stop metformin, you're good to go. If it's less than 30, you need to stop metformin up to 48 hours after administration the IV contrast and only give it again after you evaluate the kidney function test. All right? This is the takeaway from the diabetic patient on metformin. Now, for the renal function assessment, any procedure that leads to IV contrast administration needs renal function testing before giving the IV contrast. All right, you need a GFR and you need a creatinine level that has been taken 3 days prior to injecting the IV contrast if the patient is an inpatient. So if the patient is in the ward or the patient is admitted to the hospital, you need a GFR and creatinine levels in the past 3 days, right? If they're good, you're good to go, give the oral contrast, right? The IV contrast. If the patient is an outpatient, so clinic-wise or stuff like this, the patient is not in the hospital, any GFR or creatinine in the last 3 months would be good to go, right? Now, patients who are in, you would think that patients who have end-stage renal disease or the worst part or the worst type of chronic kidney disease should not take IV contrast, but yeah, only IV because oral contrast is not absorbed. All right. So you would think that patients who have end-stage renal disease or like the worst type of kidney disease should not take IV contrast, but actually these patients are already on dialysis, so it's fine. They're already on dialysis. They're getting their blood filtered, right? So you can go ahead and give them IV contrast, no problems. If these patients who have ESRD are in an emergency situation, you need, this goes back to the radiologist preference. Are there any alternatives, any ways to decrease the effect of the IV contrast on the kidney function tests? All of this goes back to the radiologist's discussion, right? Results of the renal function assessment shall be dealt with as follows. All right. Now, patients who have a GFR more than 60 can receive a normal contrast agent. And the more widely used one is the low osmolar IV contrast agent. This is what we use in normal patients and patients who have GFR that is more or equal to 60. All right. Nothing special about the low osmolar IV contrast agents. Okay. Now, the patient who has from 59 to 40 GFR, they should receive isoosmolar IV contrast. And this is one of the rare cases where we use isoosmolar IV contrast. So remember this, isoosmolar IV contrast is given in patients who have a GFR less than 59, all right? So keep that in mind. Isoosmolar is used in patients with GFR less than 59. Now, if the patient has even a lower GFR number, which is less than 14, all right? They should not receive IV contrast at all. Unless the benefits of the IV contrast outweighs the effects of the IV contrast on the kidneys. So for example, all right, you need an IV contrast to assess, I don't know, an intraparenchymal bleed in the brain, right? You don't use IV contrast in brain bleeds, but for example, right, this is a serious situation. It's an emergency situation that, if not diagnosed, can lead to death. All right. In this case, the benefits of the IV contrast outweighs the harms of the IV contrast on the kidney. So you go ahead and do it. And again, everything has to be approved by a radiologist. And we only use isoosmolar agents. So low osmolar agents are used in normal patients. Once you hit this 60 GFR mark, you start using isoosmolar. All right. Is this point clear? All right. There's prophylactic measures you can take in patients who have compromised renal functions who are receiving IV contrast. It's not mentioned here, but one of the ways is aggressive rehydration of the patient. All right. But yeah, there are multiple prophylactic measures you can take. Nothing really to talk about here. All right. So for pre-medication, all right, for allergic reactions are recommended in certain situations. However, you need to remember that pre-medication for previous reactions is not required. So if a patient has a history of an allergic reaction to peanuts 2 years ago, generally, you don't give this patient anything. You don't pre-medicate the patients before giving him or her IV contrast, right? But sometimes you might consider it, all right? Especially if the reaction was too severe. Like let's say this patient 2 years ago had peanuts and went into anaphylaxis and required intubation and went into anaphylactic shock. This is too severe to just, brush it off. You have to pre-medicate the patient before giving them IV contrast, because there's a good chance the patient will have an allergic reaction due to the IV contrast if they have a history of any allergic reaction before, right? But generally speaking, any allergic reaction, a normal allergic reaction to peanuts or shellfish zaman, does not warrant a pre-medication for IV contrast. Exactly. If the patient has a history of allergy, you don't know if this patient is not allergic to IV contrast, right? But what you do know is this patient is allergic to something. And there's a good chance that if the patient is allergic to something, he's allergic or she's allergic to something else. So you need to, So now, like I said, if you don't pre-medicate the patient, or even if you do pre-medicate the patient, just history of an allergic reaction before warrants a crash cart observation at least for 60 minutes after the injection and so on. You need to keep an eye on this patient in case they develop an allergic reaction to the IV contrast. How do you pre-medicate these patients? You pre-medicate these patients using 2 medications, methylprednisone and diphenhydramine. Methylprednisone is a steroid. Diphenhydramine is an antihistamine. All right. Now, methylprednisone is 32 milligrams PO 12 hours and 2 hours prior to the exam. So you give 2 doses, one 12 hours before the exam and one 2 hours before the exam. All right. Diphenhydramine is only 1 hour prior to the exam, and you give 50 milligrams per oral. Guys, we got a question about this. I remember it, so please remember the drugs, remember the doses, and remember the times of administration, because we did get a question about this. All right. Again, this is just memorization. There's nothing really I can talk about. Now, in emergency settings, all right, as an alternative option that is faster, because you can't wait for 12 hours to give 1 dose of prednisone and then 1 hour to give another dose of prednisone. You can't wait. So what you can do is 200 milligrams of hydrocortisone IV, not PO. The other 2 are PO. This one is IV, 4 hours before the injection, or you can give 50 milligrams of diphenhydramine IV or per oral within 1 hour of the injection. All right. And the second one, which is 50 milligrams of diphenhydramine, is the one that's more commonly used because it's only in 1 hour. So if you look at hydrocortisone, you need to leave, it has to be 4 hours before the injection. And diphenhydramine, it's only 1 hour. Administration of the IV contrast media. Honestly, guys, you just have to read it. Nothing really to explain. All right. The radiologist must be physically present when you give the contrast. You need the emergency equipment ready if in case something and anything happens, like an allergic reaction or an anaphylaxis. You need to follow policy because IV contrast is a high alert medication. Try to only stick to one vein. Don't try to puncture multiple veins to get access. Yeah. All right. So what is a high alert medication? High alert medication is medications that can cause a catastrophic side effect. All right. Those are high effect medications. So IV contrast is one. Other medications would be like, for example, benzodiazepines and barbiturates. Those two medications, they can cause severe respiratory depression and they can lead to respiratory failure. So they are high risk medications. So keep an eye out for those medications. Now, what happens once this patient develops an allergic reaction? The major reactions that you're going to see is the patient's going to start coughing, choking. The patient's going to be gasping for air. All right. You're going to start seeing swelling. The patient might start being puffy. Right. Because the patient is having difficulty breathing because of the edema in the larynx. The patient might not be able to breathe properly. So this patient might develop cyanosis. All right. And because in an anaphylactic reaction, your veins and arteries dilate, this patient can become hypotensive and get into an anaphylactic shock, all right? So these are the major reactions. Remember, respiratory problems like coughing, choking, and difficulty breathing, skin changes like rashes and swelling, and cyanosis. And the last thing is unresponsiveness and hypotension, right? Those are the major reactions you're going to see. Now, in minor reactions, you can find other things like abdominal pain, nausea, vomiting. All of these things are minor reactions to the contrast. Now, once the patient developed this, you need to do ABC or airway breathing circulation. Make sure that the airway is not compromised. These patients might need to be intubated. All right. Then breathing using a stethoscope. Just make sure that the lungs are getting air. And for the circulation is basically the hypotension and heart rate and stuff like that, all right? And obviously you need to call code blue because this patient might code on you in any second. Again, those are the minor reactions: nausea, vomiting, headache, dizziness, stuff like this, So just keep an eye out for these things. If the patient is asymptomatic after giving the IV contrast, all you do is comfort the patient, observe them for a while, and then if there's no problem arising, you can discharge the patient. And yeah, we're done with this lecture too. This is the last lecture we're going to talk about. It's 15 slides. So you guys want to take 5 minutes break and then talk about it, or just finish, get this over with? All right, let's just finish it. It's just 15 slides. All right. So the use of ionizing radiation medicine. Okay. So this is the radiation shielding is for patients. That's true, but mostly it's for us, for healthcare practitioners, right? Because the patient will have their X-ray or they're going to have their CT and then they're going to go home. It's a one-time thing, right? But you are going to be there always. You're going to do the CTs and X-rays to multiple patients, right? So you are also receiving radiation. So mostly radiation shielding is for the healthcare practitioners, all right? So yeah. Okay, so the risk of radiation exposure in medicine, and it can lead to, or it can, like, the problem is divided into two parameters. You have stochastic and you have deterministic. Now for stochastic, it's not dose dependent. So it doesn't depend on how much radiation you're receiving, right? It depends on the period of time you've been receiving radiation for. It's not dependent on the dose, it's dependent on the time, all right? Now, there's no threshold for this, like there's no cutoff point where you'd be like, oh, so after 5 hours I should stop. No, right? But examples of the stochastic effect is cancer induction, all right? So the probability of you getting cancer because of the long periods of exposure to radiation. All right. So cancer induction is one problem or one example of a stochastic effect. All right. And this happens secondary to the DNA damage. Now, in deterministic effect, this is dose dependent. So it depends on how much radiation you are receiving. All right. And this has a cutoff. This has a like, okay, once you get this amount of radiation, you should stop. Why? Because if you exceed this dose, all right, you can get direct cellular damage. And this leads to what? This leads to necrosis. It doesn't lead to cancer, it leads to necrosis على طول, because it's direct damage. So you develop necrosis immediately, right? But with stochastic, it's over the time. There's no cutoff, so you don't know when to stop, right? So it's a damage over the time. And that's how cancer arises, right? It arises over time. There's no cancer that's be like, yo, I'm here, you know? There's no cancer that arises in a day. All right, so stochastic does not depend on dose. It depends on time, right? How long have you been exposed to radiation? It doesn't depend on the dose of radiation, right? So, and an example of stochastic is cancer, right? Think about it. There is no cancer that arises in a night, right? You won't wake up tomorrow and be like, I have cancer. No, cancer takes long time to develop, right? And that's how you can think about it. Stochastic is damage to your body that is time dependent instead of dose dependent, right? So the longer you're exposed to radiation, the more likely that you're gonna get cancer or you're gonna get a stochastic damage. And one example of a stochastic damage is cancer, because it takes long time to develop, not high doses, all right? And this has no threshold. So you can't tell this patient or the doctor, yo, after 5 hours, you need to stop doing radiation or you need to stop giving this patient's x-rays, you know? There's no threshold for this. It can happen, but like the longer you are exposed, the more chance you're gonna get cancer. Now for the deterministic, it is dose dependent, right? You can get it from one procedure, right? Once you, and it has a threshold, it has a cutoff, because once you exceed this cutoff, your body is going to be receiving so much energy and so much radiation that it's going to develop necrosis. Your cells are going to die. They're not going to become cancerous. They're going to just die, right? And you can have cellular death that happens suddenly, right? In an MI, your cells will die immediately, right? They don't take time to die. They die. You can wake up in the morning with a part of your body dead. This happens quickly, right? So this is dose dependent, and that's how we can think about it. It's not time dependent, right? It doesn't take a long time to happen, but it does take a lot of energy to happen, right? So you need to be exposed to high energies of X-rays to develop necrosis and cellular death. Was this slide clear? Okay. All right, so the radiation safety principle aims to limit the exposure to ionizing radiation. This is just guidelines, you know? So you have this guideline right here, which is ALA-RA. It takes 3 things into consideration: the time you are exposed to radiation, the distance or the distance between you and the X-ray or the CT machine, and the shielding that you're wearing, all right? So you can have a lead apron on or you don't have a lead apron on, all right? So those are the 3 considerations that the ALARA takes into consideration: time, distance, and shielding. And then you have the International Commission on Radiological Protection, another guideline, and it takes 3 things extra into consideration. Justification, so why are you doing a CT scan or why are you doing an X-ray, all right? It takes into consideration optimization. So remember the KVP and the MA, did you adjust them appropriately or not? Did you optimize them or not, right? And then it also takes into consideration the dose limits, right? So basically this is just guideline stuff. You just have to memorize them. The first takes into consideration 3 things. The second takes into consideration 6 things, right? So time, obviously the less time you're exposed is related to the slit. Yeah. If you the dose limiting and the optimization happen by one of the things that you adjust is the slit thing, all right? So it's one of the things that you can adjust to optimize the dose the patient receives and that you receive. You're welcome. Now, time, obviously, the less time you're exposed to a radiation source, the less you absorb that radiation, the less the side effects of radiation on you, all right? And this is especially important for personnel such as radiation therapists. Yeah, it's just common sense. Less time, less radiation absorbed, less side effects, right? Now, the distance. This is just a fancy way of telling you that the further you stay away or the further you stand away from an X-ray machine or a CT machine, the less radiation you're going to get. It's an inversely proportional relationship, right? They did not need to write all of that. Just stay further away and you're going to get less doses of radiation. You're going to get less side effects. And that's how they do it in the X-ray machines or X-ray rooms. You know how the X-ray technician stands behind a glass door or like a separate room, you know, that's basically what distance is. Then you have the last thing, which is shielding. If you guys ever attend a coronary stenting, you know, where a radioactive an interventional cardiologist uses X-rays and live X-rays to stent a coronary artery, you will always see that the cardiologist is wearing a very heavy lead apron. It's like an apron that the doctor wears, all right? And it's made out of lead. And lead will protect the doctor from all the radiation that is coming out of the machine, all right? So the type of shielding material used rely on the ability of the material to block a significant amount of the radiation. Yeah, see, lead aprons right here, and thyroid shields and eye shields. And by the way, this is also used in pregnant women. When you need to have an X-ray for a pregnant woman or a woman or a CT scan for a pregnant woman, you can put a shield on the woman's abdomen, right, to shield the baby from any radiation, right? So it's also used in pregnancy. It's used in thyroid shields because thyroid has a high tendency of developing cancer, right? So you always want to shield the thyroid right here, right? Yeah. This basically tells you that copper has the best shielding abilities, but we can't use copper because copper is very expensive compared to lead. So we prefer to use lead instead of copper, although copper is the best, right? Exposure to medical radiation should always have a greater benefit of radiation. All right, so this is justification. This is one of the 3 things that the other guideline takes into consideration. You don't want to get unnecessary radiation or procedures to the patient unless the patient really needs them, all right? So you don't go and order X-rays right and left just because you can. You should have a good justification or a good reason why you are ordering an imaging modality for a patient, all right? So an example is a benefit in requesting a CT brain for a patient that has suffered significant head trauma generally outweighs any negative outcomes, all right? So obviously an ER, you're going to be ordering a lot of imaging, but most of the time, the benefits of the imaging outweighs the negatives, all right? So keep that in mind. You always have to have a good justification for why you're ordering something. Optimizations can be done on multiple levels. Yeah, so again, this all goes back to the CT machine and the CT technician, right? Or the X-ray machine and the X-ray technician. This can be done at a multiple levels from the equipment's design to the patient's level. All right. So as an example, requesting a CT brain. Okay. So for example, you have in the ER, the patient is complaining of a headache, right? You don't want to order a whole body CT or a pan CT. You want to only order a head CT, right? And even when you order a head CT, you can even design it even more to decrease the kVp, decrease the milliamperes, and so on, right? You can optimize the imaging that you're getting so that you decrease the harm on the patient and on yourself by optimizing the design of the machine. All right, those limits are recommended by the International Commission on Radiological Protection. This is the second guideline that we mentioned before, all right? They have cutoff points, all right? They have suggestions and recommendations for X-ray machine and CT machine settings, all right, that you can do to decrease the dose that the patient and that you are also receiving, all right? These are split into 2 groups, the public and the occupationally exposed workers. Those limits do not apply to patients. All right. So those limits, obviously, because a patient will, as I said, will get an X-ray, will get a CT, and then they will go home. That's it. You're doing this multiple times every day, so this will pertain more to you than the patient. I remember, what does the public have to do with it? Yeah, it doesn't see, the dose limit does not apply to the patient, all right? So how do I say this? The settings for the public, right? How the measures you can take to decrease the dose for the public is different than the measures that you can take to decrease the dose for yourself, right? You can do other things than the things that you're doing to the patient to further decrease the dose. You get me? You're welcome. I remember reading that this was skipped. Wait a second. Yeah, it says here, no need right here. So I didn't really bother. All right, and this should be the end of it. You guys have any questions? Are we good? You're welcome. All right, great. I think we're done with the lectures today. All right, tomorrow, inshallah, we're going to go through those four lectures: the introduction to CT, the clinical applications of CT, ultrasound, and preparation, inshallah. All right. Thank you for attending, and see you tomorrow, inshallah. You're welcome.